In case 1 and 2 of our t-test, we specified that we had to be able to say with some confidence that there wasn't really going to be a difference in how variable the two sets of data that we were comparing were. One, we knew it wasn't going to be very different because we said it was against the standard in case 1, and that one didn't have any variability, since we used a well-known standard reference material. Case 2, that was when we said, yeah, they're different populations, but we're pretty sure they're going to be the same. And you remember I gave the zinc in soup versus zinc in tea leaves example. That's actually a real assay, by the way. Now in this case we say, wait a minute, what if we were actually testing to see if methods had a difference in their outcomes, in their variabilities? In that case, we actually have to make the assumption that there could be a difference in the variability, since that's one of the things we want to know. Or if we already know in advance that we're using two different approaches, that's a good sign that we're going to need to use this sort of a case. Maybe we're using an atomic absorption spectrometer to measure a digested sample on one, and in another one we were using, I don't know, let's make something up, maybe an X-ray fluorescence instrument to measure the zinc fluorescing in in the tea leaf in the chicken soup. Very different outcomes in terms of how the physical phenomenon does the measurement, so there might be some hiding variables that are going to throw things off. To test to see if the variances are different, we use this pair of equations. We have to determine a new sort of standard deviation for this one. Now what we're going to do is we're going to pair up a bunch of measurements. We're going to do a bunch of measurements with method A, and then a bunch with method B. We're going to go back and forth. We're going to keep each of those values logged next to each other in a table. If you'd like to see a copy of that, we have on page 62 of the 7th edition, and on page 78 of the 8th edition of the Harris textbook, you'll see a set of data as an example where they take method 1's number, method 2's number, and here I'll just do it like this. There's number 1, there's the number measured by method B, we subtract the 2, and that gives us a difference. We rinse and repeat for each of the individual measurements that we have in there. That's going to be what you see right here. Difference between the individual measurement and your average difference squared over our degrees of freedom. Take the square root. That's going to be this SD term. We then come down, we plug that in right here. We have our average of all these D's over top of our standard deviation times the square root of n. So you can see that it's a much more complicated setup. We actually are taking the entire concept. It still works the same way conceptually, but we actually have to break the equation apart and handle each of the pieces piecemeal and then pull it back together in the end. In this course, we're typically not going to be doing case 3 methods, but that would definitely be something important if you're actually running some sort of an instrumentation lab and you're trying out a new instrument, or if you're running some sort of a biomedical research facility or a core facility at a medical lab. If you need to test to make sure that your analysts are working the same way, different methods are working the same way, whatever, that would be this case 3 t-test, and so you'd end up getting a little bit more gory experience with it there. At that point, though, the distinction really is just a matter of plugging the same sorts of numbers into a different kind of equation. And since there's nothing new conceptually to be learned from that process, and since that's outside of the range of this course specifically, we're going to just leave it at that with this explanation that that's a case 3 t-test.